Welcome to Joe's Classroom. In this video, I'm going to explain the convolution of signals in discrete time domain using an example. Before taking up the example, let us have a quick review of the concept of convolution in discrete time domain. Let us consider an LTI system. By LTI, we mean it is a linear time invariant system. If I give any input to this system, the system has to respond and it has to give me an output. For a while, let us assume that we are going to give an unit impulse signal as an input to the system. You should be knowing an unit impulse signal is defined as delta of n is equal to 1 for n is equal to 0 and 0 for all values of n not equal to 0. Graphically, it can be represented like this. For n is equal to 0, it is going to be 1, and for all other values of n, it is going to be 0. Now, if I give this unit impulse signal as an input, the system has to give me a response, and let me call the response as h of n. Since h of n is the response of this system for a unit impulse input, we will call this response as an unit impulse response. Also, let us assume that for the given system, this unit impulse response is known to us. Now let me take the same system and give an arbitrary signal as an input to it. Of course, the system has to respond and it is going to give me an output. Let me call the output as y of n. Let me ask you something. For this arbitrary input x of n, can you find y of n, that is the output? You will immediately tell me that if I know something about this system, if I know what is this system or how this system responds or behaves, I can find out y of n for the given x of n. But my question is, I do not know anything about this system, but what I know is, I know its unit impulse response, and being an input, I know this input also. Therefore, my question is, if I know only this unit impulse response of the system, can I find the output or the response of an arbitrary input? The answer is yes. Here is where the convolution sum comes handy to us. Y of n is given by, the convolution sum is given by the summation from k is equal to minus infinity to plus infinity, x of k, h of n minus k. So when we look at this expression, it is very clear that y of n is found from x of k obtained from x of n and h of n minus k, which we can obtain from h of n. Therefore, to find out this y of n, what I should know is this x of n and h of n. Or otherwise, I can say that to find out the response y of n for an arbitrary input x of n, the only thing that I should know is h of n. This enables me to say that this LTI system is completely described by this h of n, because if I know this h of n, that is unit impulse response of the system, then I can find out the output of the system for any arbitrary input. I need not know anything else. Therefore, again I can say this h of n completely represents the system, or I can say the LTI system can be represented by this h of n. In fact, this convolution sum is obtained by exploiting the properties of the LTI system, that is, the property of time invariance and the property of linearity. Therefore, this convolution sum is valid only for LTI systems. And the literal meaning of convolution is rolling or coiling together. If you look at this expression, it is very clear that this summation, through this summation or through this operation, what we do is we combine x of k and h of k, or x of n and h of n together. We roll it together. We roll them together to get this y of n. That is why this is called the convolution sum. Now, as I said, this system is now represented by this h of n, and y of n is obtained by the convolution of x of n and h of n. This convolution sum can be represented in this manner also. This asterisk mark says that the signals x of n and h of n are convolved. Or otherwise I can say that the signals x of n and h of n are subjected to an operation called the convolution. An interesting thing is, here the system, that is the LTA system, is represented by a signal, because h of n is the output signal of the system for unit impulse input. Now let us expand this convolution sum. If I expand this convolution sum, it may look like that it is going to have infinite number of terms in it, but it need not be so always. Let me explain it with an example. Let us assume that this is going to be my x of n, and this signal x of n has to be convolved with this h of n, that is the unit impulse response. Obviously, x of n exists only for n is equal to 0 and n is equal to 1. That is, x of 0 is equal to 0.5 and x of 1 is equal to 2 and x of n is equal to 0 for all values of n not equal to 0 and 1. Therefore, in the entire expansion, there are only two terms going to remain. The terms containing x of 0 and x of 1. That is this term and this term. All other terms will be equal to 0. Now let us take this example. Let us assume this is going to be the unit impulse response, or the h of n. I am going to give another input to the system, that is x of n, which we took in the previous slide as an input. For this input, I need to find out the output y of n. So, obviously, what we have known is this h of n and this x of n. From the discussions we had, we can represent this LTA system by this impulse response h of n, and the output y of n is given by the convolution of the signals x of n and h of n. We can write the convolution as a convolution sum, and in the previous slide we understood for this x of n, the convolution sum is going to have only two terms containing x of 0 and x of 1. We know that x of 0 is equal to 0.5 and x of 1 is equal to 2. Therefore, the summation can be written as y of n is equal to 0.5 h of n plus 2 h of n minus 1. So if we know this h of n and h of n minus 1, immediately we can find out y of n. H of n is already available to us. What is going to be 0.5 times h of n? All the terms in h of n have to be multiplied by 0.5. So all the magnitudes will become 0.5, and this is what you will get. Now you need to find out 2 times h of n minus 1. This is what is your h of n minus 1. H of n shifted by one sample or delayed by one sample, and it has to be multiplied by 2. All the terms in h of n minus 1 have to be multiplied by 2, and you get 2 as the value for all the terms in 2 times h of n minus 1. Now what you need to do is you need to add this signal and this signal to get y of n. So this is what you do y of n. For n is equal to 0, there is only one stem of value 0.5 corresponding to the first term, and therefore the resultant value will be 0.5 for n is equal to 0. And for n is equal to 1, it is 0.5 plus 2, so it is going to be 2.5. And for 2 also, it is 0.5 plus 2, that is going to be 2.5. And for n is equal to 3, it is 0 plus 2, that is going to be 2. And for all values of n greater than 2, the summation is going to be 0. Therefore, we get y of n as shown in the last figure. So we got the output y of n by convolving x of n and h of n. This is what we call as the graphical convolution, because we convolved the signals x of n and h of n by sketching the signals appearing in this convolution sum. Hope you understood about the graphical convolution of signals in the discrete time domain. If it is so, you may like, share or comment.